Okay, recording. Now, for a test, I will take some time a little bit to talk about individual problems and common mistakes that occurred. So, as I mentioned before, each problem of any kind is for 15 points. So, after deducting points on the first 7 problems and not bonus, I subtracted that from 105. This is 15 times 7, and added on any bonus points. When I did that, the average fell somewhere in the low 60s, so I just bumped all the scores up by 12 points. So that takes the average around 75. I will not always, so I didn't want anyone's grade trash too much in the early stages, but not much of your grade is really determined at this point. I would say about only 20% of it. There's a lot more homework left. There's 2 more tests plus a final project. So if your grade's low at this point, there's plenty of time, plenty of opportunity to raise it. Anyone just coming in, you can, after class, or you can do it right now is fine. There's only 2 of you. But what's your last name, please? Stringer. Yes, sir. And, okay. But I saw quite a bit of carelessness that I think needs to be addressed. In a nutshell, you guys need to up your game for the next time. So hopefully when I discuss these problems, you'll understand why I said that. Okay. Now, you may see, well, actually, you will see at least some of these problems on the final, because the final is comprehensive, but it would only be a portion of it. Okay. Now, I won't have time to go through each problem in full, but at least indicate how to go about it and how to finish from there. So first one, the application problem. So I mentioned certain possibilities. The practice test had a mixing problem. It was kind of strange to see some of you write things about mixing on this problem when it wasn't about that. Redirected decay, population growth, or financial applications, all of which we've seen examples of at one point or another during class. The problem states, write down a differential equation that models S of t. Therefore, I intended for you to write down a differential equation. Not many of you did that. The equation, which is one that we have seen before, is this one. I don't care about the choice of letters, but anything of this form, where S, in this case, represents the total balance remaining. R would be the interest rate, given to be 4%. And then K, because you want the balance to be decreasing, K is going to be a negative amount, reflecting how much is paid. Now, I gave you a monthly payment amount of $700, but the interest rate is given in years, and all the other information in the problem is given in years. So K should be minus 8,400, 700 times 12. So that's how much is paid per year. And then the initial condition is actually the unknown. That's what you're needing to find. Really what you're given is not an initial condition, it's an end condition. After 30 years, the balance should be 0. Now, this is a linear equation for which you have a solution formula, but I also gave a solution formula specific to this case where R and K are constant, so either approach would have been fine. I saw some of you write down solution formulas that did not bear much resemblance to either. So if your preparation involves taking time to memorize these things, that's a good idea. But I'm concerned about the reliability of that memorization. But it's also why I provide a formula sheet for certain things. So if you didn't use a solution formula for this case directly, where R and K are constants, the one on the formula sheet would have been fine too. Okay, so what you would do is, once you have a solution for S of t, you plug in t equals 30, and you set the result to 0. So you solve for the initial value, which I'll refer to as S naught. Turned out to be just shy of $150,000. Okay. Number 2 went pretty well for the most part. Well, I do have some concerns, well actually, not just for this problem, but for the test as a whole. And it doesn't seem to matter what the class is, whether it's something from a calculus sequence or differential equations, or whatever it is, the weakness always seems to be in the algebra.
For that first y, it's y cubed, not y squared.
Yes. I just got these classes. Dang it. Okay. So you're supposed to identify the equilibrium points. So that would be y equals 0 and y equals 4, coming from setting each of these equal to 0. Now, a significant number of people wrote down y equals minus 4. But 4 minus 1, thinking I got factorizations like this. That is incredibly wrong. If it had been a little different, and maybe you're thinking of this situation, that is a difference of 2 squares. That could be factored into, what can that be factored into?
2 plus y minus y.
Yeah, 2 minus y. Actually, no one put that as an answer, which is a good thing. But so, difference of squares, square of a difference. Know of a difference. Okay. And then from this equilibrium, then this situation, if you look at the sign of y prime, positive or negative, this is unstable, stable, and then if its arrows going in the same direction, either both up or both down, that is semi-stable. So I saw a number of cases of misidentification. So even when the arrows were correct and the equilibrium were correct, that this classification was still off. Questions about these first 2? Yes?
For number 1, what did you say the answer was?
It's just a little under $150,000.
What did the phase line look like for number 2?
At 0 and 4. 0 turned out to be unstable, say the arrows going in this direction. 4 turned out to be semi-stable, so both the arrows going up. Other questions about the first 2? We're just solving some differential equation with the initial condition. I gave a substantial amount of credit simply for identifying which approach you're supposed to use, even if carrying out that approach did not go well. Since which approach to use, an important task is figuring it out from the form of the equation. Math, any math class is so much pattern matching. Certainly this one is. Okay, the third one. This one went relatively well. Y prime plus 2y is equal to t e to the minus 2t with an initial condition of 1 equals 0. Now, this is a linear equation, and I believe most people correctly classified it that way. But a number of things went wrong after that, because your solution formula, so the integration factor, is e to the integral of this coefficient. Now, note about the general form of a linear prime plus p of t y equals q of t. So you have y prime, you have something multiplying y, that's the p of t. Whatever sits on the right side, that's the q of t. So p of t, whatever is multiplying the y, goes in there. Not the y. Leave out the dang y. And I'm saying this because if you did this, trust me, several of your classmates did too. And I have enough gray hairs as it is. So e to the 2t. There isn't going to be any y involved in the integrating factor. It's a function of t only. And that was chosen so that things will work out nicely on the right-hand side, because you got to multiply both sides by e to the 2t, so you get your q times the integrating factor. So your integrating factor of t e to the minus 2t. Now, a lot of people got to this point, okay, and didn't realize these cancel out. They're doing all kinds of crazy integration by parts or who knows what. At some point, I just couldn't bear to read it. Those go away, and they left with the integral of only t. I was thinking, well, the problem is, look rough up front, but once you actually work through it, I'm not giving you some nasty integral to work out, because I didn't want to do that. Okay, and if you got this far, then pretty much everybody, of course, would integrate t squared over 2, and what am I supposed to throw in there? Plus c. And this is what really doubled my gray hairs. All of that, including the plus c, is multiplied by the e to the minus 2t. I recall mentioning that, like, when you have this kind of problem, whatever you have up front multiplies everything. I've said it several times to say it. Again, I'm not singling anybody out a number of times, and it's like, so these are the unforced errors that need to be cut down on. Okay, and you give an initial condition, you use that to figure out the c. C turns out to be minus 1/2. Questions on that one? Number 4. dy dx is 3y squared plus 2xy over 2xy plus x squared. How is this to be classified? It's a homogeneous equation, because every term involved has the same degree, that v equals y over x. So you divide top and bottom by the highest power of x throughout, which is x squared. So what you get is, after some algebra, 3v squared plus 2v over 2v plus 1. But then, what has to be done at this point is, you have to rewrite y prime in terms of v prime. So vx is equal to y. You differentiate both sides of this. Well, you also give it a solution formula, but v prime x plus v x prime, which is 1, is equal to y prime. So y prime on the left has to be replaced by this. v prime x plus v is equal to the rest. And I'm just going to move the v to the other side. When you put everything over a common denominator, on the right, you get something that can be worked through. Now, again, I won't go through all the details of this. The point of this transformation is to make the differential equation separable. We see we have this x here. So you would get 1 over x dx on the right side. And then if we flip this, move it over to the left side, you get, after all the algebra, 2v plus 1 over v squared plus v dv. And both sides. This problem was contrived so that the top was a derivative of the bottom, so you could use a substitution. It was perfectly fine for this to leave the solution in implicit form. It was not necessary to solve for y. Okay. All right. Questions? All right. Okay. Yes.
What happened to the, like the 3v squared plus 2v? What happened to the constants?
That common denominator.
Oh, okay.
And then once you simplify all this, you get n, divide by it to move it over here, you get that.
Yeah, that makes sense.
Okay. Other questions? All right. 3 problems to go. I'll like to talk a little bit about the bonus too, but okay. Number 5. This one can actually be worked out 2 different ways. Now, what I had in mind was to treat it as an equation solved as if it was an exact equation, but you have to check if it's exact first. Okay. And this equation, if you were to rearrange this to write it as dy dx equals something, notice every term has the same degree of 2. It could have been done as a homogeneous equation also. I don't care which approach you use. But this is the way it's written. Most people will realize, okay, you need to check if it's exact. And then, what if it is not exact? What do you do? Yes, using what? Integrating factor. I saw a few cases of people correctly concluding that this equation is not exact, and then solving it as if it was exact. You need to get the integrating factor. Now, but that wasn't the first thing that went wrong for a number of people. So this is your m, and this is your n. So you compute the derivative of m with respect to y. So here we have x is treated as a constant, so here we have 3x, and we differentiate that with respect to y. A lot of people did not get this, like this term was left out. Like it's a function of y. It has a derivative, so that needs to be in there. Derivative of n with respect to x, so x squared will give you 2x. Y is treated as a constant because you're differentiating with respect to x. So you get y. If you do not see y goes over derivatives of m with respect to y and n with respect to x, then that's something that should be brought to my attention. Again, if you're differentiating with respect to one variable, the other you've treated as if it was a constant. So for example, here I'm taking derivative with respect to y. If this had been x squared, then yeah, I'd have nothing. I'd have 0 for that. But since it's y squared, we get a 2y. So they do not match, so it's not exact. Now, one really disturbing thing I saw, again, by enough people to bring it to your attention, was that some people wrote down the my and nx from the practice test. Because I was like, why are so many people writing 1? Where's everybody getting 1? Like, oh, I looked back at the practice test and that's what it was. At that point, you're just not thinking. Right? The prerequisite for this class is Cal 2. Therefore, you all know how to take a derivative. And also how to work an integral. So, I give a practice test to give an idea of types of things, not the exact things, but the types of things that you should be able to do on a real test. It's not the first time that I've seen instances of people just taking what was in the practice test, even though it's a whole other problem now. Right? I'm showing you these methods, from the examples done here in class, or when you're doing the homework on the practice test, and you go execute those methods, something from an unrelated problem on something else. Right? Again, that's just not thinking. You wouldn't have made it into this class in the first place without being better than that. So, I could always prevent that from happening in the future by not offering practice tests, but I imagine you wouldn't like that either, would you? Then use the practice test appropriately. So, what I will do going forward is for the final, which will have practice tests. If someone carries out of a problem as they're supposed to, but then makes a mistake, then there's a certain amount of points deduction, but there's partial credit. If I see an instance of you simply taking what's done in a practice test, blindly and just using it, even though it doesn't apply to the problem that you're given, that will result in a higher deduction than if you just made an ordinary mistake. I'm not playing. I also want to point out that, not related to that situation, since I had a graduate student, Chandler, proctoring the test, and she reported to me that there was some suspicious behavior in this room during the test. If I see that continue, I'm just going to give someone an XF grade. All right. If you don't know what an XF grade is, because it's relatively new, it indicates failing through academic dishonesty. And it cannot be erased from your transcript even by repeating a class. It will be there forever, saying that you committed academic dishonesty. Don't play games. Show up, do the math. That's it. So again, I'm not playing, don't you either. I shouldn't have to bring that up. Okay. This is not exact. An integrating factor is required. So what you examine is my minus nx over n, nx minus my over m. And if this one is a function of x, or this one is a function that can be used as the integrating factor. My minus nx is going to be plus y over n, which is x squared plus xy. You correctly got that, and then didn't think it could be used as an integrating factor. You have to simplify as much as you can. Because notice down below, you have a common factor of x that can be pulled out. The x plus y's cancel, and you're left with 1 over x. Therefore, the integrating factor of a function of x is e to the integral of that, which is e to the log x, which is x. So x turns out to be the integrating factor. So if you multiply the original equation through by x, then you will get something that is exact. You can see here you have similar terms, something times x plus something times y in both cases, but the coefficients didn't match. Multiplying through by power of x or y changes those coefficients, and it turned out multiplying by x makes them match. Okay, and from there, the new equation is 3x squared y plus xy squared dx, that is your new m, plus x cubed plus x squared y dy is equal to 0. So the solution formula is, I said m1 to be the integral of m with respect to x. And y is treated as a constant. So y here is treated as a constant. You're integrating 3x squared. But what is the derivative of 3x squared? X cubed. So you get x cubed y. And then you integrate x, and you get x squared over 2 times y squared. So that is your m1. From there, you need to integrate. Okay. So the other part of your solution. So this is one part. So that's part of your solution right there. To get the rest of it, you integrate n minus the derivative of this that you just got with respect to y. Okay. And I saw some instances there of this problem and a similar problem, number 7, where also an exact equation where you things were off with the integrating. Again, keep in mind which variable you're integrating with respect to. Like you see, for instance, like a x squared, you might think, oh, it's x cubed over 3. Well, yes, if you're integrating with respect to x, but if you're integrating x squared with respect to y, then it's just x squared y. So the first time, it's with respect to x. Second time, is with respect to y. So you take a derivative of this with respect to y, and you get x cubed, so minus x cubed, and then minus x squared y. And what's supposed to happen at this point is everything that depends on x cancels. Well, in this case, that's everything. All of it cancels. So you get the integral of 0 dy, which is a constant. So the final answer is, this first part is m1, x cubed y plus x squared y squared over 2, plus a constant is equal to 0. Okay. So this is one of your checkpoints when you're going through this. If you're working this expression out, this is kind of a mess, and if there's anything in there that depends on x, you know that something went wrong. Questions about this one? Number 6, y prime is equal to xy cubed over square root of 1 plus x squared with an initial condition. How is this equation to be classified? What are the types? No.
Separable.
It is separable. Or homogeneous need all terms to be the same degree. This degree 1, actually they're all different degrees. This is separable. Now, there were a number of people who correctly, or from what I can tell anyway, with their work, correctly identified it as separable. But, you got to think about what that means. That this right side can be separated into function of x times function of y. So, if I write it this way, just a little spacing. Okay, so now you can clearly see function of x times function of y. And then everything with y, one side, everything with x, the other side. That means you have 1 over y cubed dy. It's equal to x over square root of 1 plus x squared dx. So you can integrate both sides. I saw, again, a number of cases where these integrals were written down, but there'd be things with x on this side, or things with y on this side. And again, several times, that's what separable means. Everything with one variable on one side, everything different variable on the other side. Separated. Otherwise, what are you going to do after that, integrating both sides, simply isn't going to work. So for left side, power rule, this can be done with a u substitution. U is equal to 1 plus x squared. So then du is equal to 2x dx. And sure enough, you have an x dx right there. Okay. Final answer in implicit form is y to the minus 2 over minus 2 is 1 plus x squared to the 1 half minus 3 halves. So you have plus c, and then c turns out to be minus 3 halves. One other thing that came up again by more than one person, when you do a substitution, you get something like this. You get basically u to the minus 1 half du. And there's a constant outside, but I'm just focusing on this part. Now, some people did at this point, or maybe they had it written this way. 1 over u to the 1 half. Yeah. And then they did this. ln u to the 1 half. The integral of 1 over u is natural log of u. The integral of 1 over anything is not ln of anything. Necessarily. It's only in that one special case where it's 1 over u. This calls for power rule, because you can write it as u to the minus 1 half du. So then you get u to the plus 1 half over 1 half. So that's how that needs to be handled. Okay. Questions about this one? Okay. The last one is similar to number 5. It has that kind of appearance: 3x squared minus 2xy plus 6y squared minus x squared plus 3 dy. So this is treated as if it's hopefully an exact equation. This one actually does turn out to be, because dm dy, well, the only term it depends on y is this one. So you get minus 2x. Here you take a derivative of n with respect to x. So ignore that. You have minus x squared. Derivative of that is minus 2x. So everything works out. You don't need an integrating factor. This problem went relatively well, because you would take the integral of this with respect to y. That was x. Sorry about that. So we would get x cubed, and then y is treated as a constant, so you have minus x squared y and then plus 2x. Okay. When you take the derivative of this with respect to y, all the terms are ignored except for this one, minus x squared y, so you just get minus x squared. But then you would take this minus this and you integrate that with respect to y. Notice you have minus x squared in both, so they cancel. Okay, so your function g of y is integral of 6y squared minus x squared plus 3 minus x squared dy. And as I just mentioned, these cancel. It looks more like a dy. So what you do in integrate this with respect to y, you get 2y cubed plus 3y plus a constant. So then this plus that is your solution. Set equal to 0 is your solution. Questions about this one? Okay. Admittedly, the bonus was a bit of a curveball. That's why it was a bonus. Because it uses a similar idea as one of the previous problems, but with a twist. Y prime plus 2y is equal to y squared. So it cannot be handled. This is a nonlinear equation. That's everything. I think the separable equation had a y cubed in it. Some people try to treat it as a linear equation. Linear equation, you have y prime plus a function of t only times y, just plain y, is equal to some function of t. The left side fits the form of a linear equation. The right side doesn't. So for linear equation cannot be used here. So I gave you a substitution. Y is equal to 1 over v. And the thing is, what you get from using a substitution, y prime plus 2 over v is 1 over v squared. But then you got to replace the y prime. So what I could do is say y prime is equal to minus 1 over v squared v prime. So that is what goes in there. And then you have all these v's in the denominator. So if you multiply both sides by v squared, then what you get is v prime minus 2v is equal to minus 1. So as I mentioned in the problem, when you make a substitution and get a new equation, it's a linear equation. So you could use the usual approach of an integrating factor and so forth to work that out. If you want to try your hand at it and see if you can get it, the final answer is supposed to be 2 over 1 plus a constant times e to the 2x, once you put everything back in terms of y. Okay. All right. Questions about the test? Yes?
Is there like gonna be an answer key that we can look at where they're like worked out so we can check and see where we went wrong?
I think I could do that in this case. I'm not going to promise it for every single test, but I have enough info written down where I can produce it pretty quickly. Other questions? All right. Now, unfortunately, things move on. There's still plenty to cover, which I'm going to get a start on as much as I can today. And of course, because of the test, and break it so forth. If you haven't had any homework in a while, I will have. I do have new assignments that are ready to post, which I will do later today. When they will be due depends on how far I get today. It will either be Thursday or the following Monday. Alright. Everything we've done up to this point has been about a first order differential equation. So y prime is equal to something, some function of t and y. Now we're going to allow higher order derivatives. We're going to focus almost exclusively on second order, because from first to second order, it is a huge difference in what you do. Also, whereas before we looked at first order equations that were either linear or nonlinear, I'm going to focus exclusively on linear. So the approaches that we see for solving these kind of problems, at least in terms of appearances, be drastically different than what you've seen so far from first to second order. From second order to higher order, linear, it doesn't really change that much. Okay, so we need to establish some terminology, notation, etc. So the problem we're going to be looking at is y double prime plus some function of t only, y prime, plus some function of t only again, times y is equal to some right-hand side, g of t. So it's somewhat similar to the linear equation you saw for its first order. You had y prime plus p of t y equals q of t. So it's kind of like that, only you have derivatives, a second derivative involved. Okay, so the p and q are coefficients. In most cases, they will be constant. The certain solution methods we will see will only work for p and q constant. Now, here's an unfortunate choice of jargon that you need to be aware of. So this equation is said to be homogeneous if g of t is equal to 0. It is not related to the homogeneous that we saw before, and I just use them. Now, I can promise you that this unfortunate ambiguity is not going to be something that will get in the way of working any problems. So really, until we get to, actually forget the previous meeting and just go with this one. Because we're going to start with a case where the right-hand side is 0, learn how to solve that. As we get towards the end of the chapter, we'll allow g to be non-zero and figure out how to solve it in that case. Okay. Now, we have initial conditions. So y of 0 is equal to something. Prime is 0 is equal to something. Or it could be some other initial time, but almost always it'll be 0. Now, we need two initial conditions because it's a second order equation. So whatever the highest order derivative you have in the equation, whatever the order of it is, of the equation is, that is how many initial conditions you need to solution. Now, another problem of interest is where you have, instead of having two initial conditions, you could have what are called boundaries. You set the value of y at one point, and you set the value of y, not y prime, y at a second point. Either way, you have two conditions, and that will establish a unique solution. In this class, we're just going to deal with the case of two initial conditions. Now, there is, just like the first order equations, an existence uniqueness theorem. And the main idea behind that is, okay. So the initial value problem, IVP, has a unique solution on an interval that I'll call I, containing the initial time t naught. Here I said t naught equal to 0, but whatever the initial time is, t naught, you have a unique solution on an interval containing that initial time, which is what you want anyway, if all the functions of t involved, p, q, g, are continuous on that interval. So for example, if p of t is 1 over t, then you have a problem at t equals 0, because it's not continuous, not even defined, let alone continuous there. So, as I said, in most cases, p and q will be constants. So generally, problems dealing with, you can be assured that there is a unique solution. What complicates matters is what form does that solution have? Okay. Now, introduce more help needed notation. So here's a shorthand for the second order differential equation that I was just talking about. Ly is equal to g, where what is L of y? It's y double prime plus p of t y prime plus q of t. And g is the g of t from over there. So L is what is called a differential operator. So what is a differential operator? It's a process you apply to a function, in this case y, that involves taking derivatives, multiplying by functions of t, and adding up. So what's being done to y in this case? Taking the second derivative, adding q times the first derivative. Oh, I forgot the y here. Adding q times y. All of that process, going from y to this, is applying a differential operator L. So that equation over there is written as L of y is equal to g. So it's a helpful shorthand. Now, to solve this equation, we need to work with the corresponding homogeneous equation. And that's just L of y is equal to 0. So the solution of this helps us get the solution to the original. All right. Just want to make sure I'm not missing any terms that we'll need later. So, now I can describe to you at least the form of the solution, which is the first step towards being able to get a solution. So the formal solution is y of t is equal to a constant that I'll call C1, y1 of t, plus C2, y2 of t, plus yp of t. These first two terms here I'm going to abbreviate as y sub h of t, h for homogeneous. So YH is called the homogeneous solution. And it is the general solution of the homogeneous problem. Ly is equal to 0. So what do you get just from setting the right side at G equal to 0? So all solutions of the homogeneous equation have this form, where C1 and C2 are allowed to be any constants whatsoever. How do you get the constants? From your initial conditions. You have two initial conditions, you have two constants to find. Just like with linear problems before, you had an initial condition, you had a plus c in there somewhere, and you used the initial condition to find out what this plus c was. Okay. Now what is this? This is called a particular solution. That's why the subscript p. Of the original equation, Ly is equal to G. So I'm writing Ly all over the place because I don't want to keep writing y double prime plus p of ty plus q, p of ty prime plus q of ty all over the place. I'm using this shorthand, but it's important to keep in mind, what does that mean? It's just the left side of the second order equation. Okay, so when we're solving this problem, so some given second order linear equation, first we focus on the case where G is 0, if it's not already given to us as 0, and we find these, which is the topic of the next few classes. Then we find a solution of Ly is equal to G. It doesn't describe all solutions, it's just one solution. And toward the end of the chapter, I'll show you two techniques for getting that. And then we put them both together, and now we've described all solutions to Ly is equal to G. If you're given initial conditions, then you can use them to figure out values of C1 and C2. So our focus for the time being is going to be on this y1 and y2. So two of them together, y1 of t and y2 of t, or it could be functions of x, depending on what's given, is called a fundamental set of solutions. Of the homogeneous problem, Ly is equal to 0. It's important that these be distinct. In other words, one is not a multiple of the other. So like e to the t, bless you, e to the t and 2e to the t, that would not work as a fundamental set because one's just twice the other. But if you have two what are called linearly independent solutions, then that constitutes a fundamental set. Because then we can use those two to describe all solutions. Okay. All right. So going forward, what I will do is for certain cases, I will show you how to get y1 and y2, and really boils down to solutions of a quadratic equation. So then you can solve this problem, and then later on we'll figure out how to get particular solutions. Now, how much time do I? Okay. But first, I'm going to show you a technique for second order equations called reduction of order. Okay. Now, so this is for a specific situation. Suppose this is what you're given. You're given a general homogeneous second order equation. That's a 0 on the right hand side. And you're given a solution, which I'll call y1 of t. So that's how the problem is described. You're given that this function, whatever it may be, is already known to be a solution of this. What do? Well, your task, find another solution, y2 of t. So in other words, you're given half of a fundamental set, and your job is to find the other half. Okay. And how you do that is this technique called reduction of order. And I want to make sure to get to a solution formula for y2 before we finish today. Here's what you do, though. You assume a certain form for y2. You assume that y2 of t is equal to your previous solution, your known one, y1 of t, times some unknown function I'll call v of t. So really what you do is you find v, and then once you have that, you multiply by y2. Now, why this helps, and I should mention that 4.2 is a section in the textbook. In my notes on the resources page is section 3.2. And that's where you'll see whatever details I don't give here. Because, again, it's not something that you would use for working on problems. You want a solution formula that I will arrive at shortly. Okay, but what you do is you take this form, y1 times v, and you substitute it into here. And you simplify it, keeping in mind that y1 is already known to be a solution. That causes a lot of terms to drop out. So when you do that, as much as you can, then you have this equation for v double prime plus 2y1 prime over y1 plus p of t times is equal to 0. Now, it looks like we have an equation that is no easier than what we started with, because we have a second order equation here, and now we have a second order equation down here also. But there's one huge difference. There's no v term. That has been made 0 as a result of this substitution. So this may be a second order equation in v, which doesn't help us, but is a first order equation in v prime. So in other words, if you create a new variable, like say w is equal to v prime, equation in w, we know how to solve that already. We can use solution formulas from the previous chapter. So what that tells us is, if I let w equal to v prime, then I can say that W prime is equal to minus all that stuff in parentheses times W. And therefore I know what W is. So WT is e to the minus integral of 2y1 prime over y1 plus p dt times the constant. But any multiple of a solution is also a solution. So I'm just going to say the constant is 1. We're not trying to nail down a unique solution here. And a lot of simplifying can be done here with this, because this integral, y1 prime over y1, the integral of that is natural log of y1. So a lot of simplifying the properties of logs can be done, and I'll just cut to the chase here. We get 1 over y1 squared times e to the minus integral of p, and p can be anything, so I can't work that out. But for a given p, you can. So that's W. W is V prime. Well, I need V, so I need to integrate that. So I'll just write down your solution formula. Y2 of t, so in other words, this is your final answer. It's y1 of t times the integral of y1 of t squared e to the minus integral of p dt. So for a homework problem you're given, using reduction of order, you're given an equation like that, you're given y1, and p of t is whatever is multiplying y prime. Grind this out, and then that's your answer. Notice this y1 is outside the integral, this is inside. Because the integrals are with respect to t, I cannot just move this in. So you have to work out this integral first, simplify as much as you can, and then this integral second, and then multiply by y1 to conclude. So that is the, I'm going to move this a little bit so anyone not here can see the solution formula, but I have enough time for examples. So now, and when I do the example of, or how many examples I counted, I will repeat the solution formula here. So, as an example, here's your second order equation: t squared y double prime minus 4t y prime plus 6y is equal to 0, and you're given a solution y1 of t is equal to t squared. So if you were to substitute t squared into here, you would get 0. So so your job is to find y2 of t. Now before you begin, rewrite the equation so that the y double prime is by itself, coefficient of 1. So you divide both sides by t squared. And you get y double prime minus 4 over t y prime plus 6 over t squared y is equal to 0. So then this, whatever's multiplying y prime, that is a p of t you need in the solution formula. So be sure to divide first if you need to before you apply the solution formula. Otherwise you get something wrong. So here's the solution formula I had on the other board. So first a general case. Hopefully this is still going. Hello? Do not do this to me. Okay. So it's y1 of t times the integral of 1 over y1 of t squared times e to the minus integral of p of t dt. So now I just need to fill in all the particulars. So y1 of t is t squared. 1 over y1 squared, behind the integral sign, that's so it's 1 over t to the fourth. And then I have e to the minus 4 over t. So the minuses cancel. So now, we integrate that. So 4 over t was the integral of 4 over t. Come on.
Visited for.
Yes. Yeah. You have a 4 natural log of t, but the 4 can be moved over here. So that's the same as e to the log t to the fourth. The e and the log cancel. So I have t squared integral of 1 over t to the fourth times t to the fourth. And those cancel. This happens a lot in these problems. You get a lot of simplification happening. So now I have t squared times the integral of 1 dt. So you have t squared times t is equal to t cubed. And so that is your final answer. That completes the fundamental set of solutions. So t squared and t cubed, those are enough to describe all solutions of this equation. Now, you may notice that even though I worked out 2 integrals in this process, I did not include any plus c's. The reason why is I could, but it would be redundant. If I include a plus c in this integral, what do I get? y1 times something plus a constant times y1. But I already know that y1 is a solution, so it doesn't really contribute anything. So in doing these, in the integrals that are involved, there's no need to include a plus c. Questions about how this one was worked out? All right. I have just enough time quickly for one more. And there's a third one in the notes. So the homework for this section basically consists of these problems. You're given some second order equation, you're given y1, and you find y2. Yes, I hear you guys getting restless. Still have 2 minutes. Y double prime minus 5y prime plus 6y is equal to 0, and y1 given is e to the 2t. So then you find y2. So the solution formula again. This minus 5 is your p, which is a constant in this case. So y2 is, again, solution formula. y1 integral over y1 squared e to the minus integral of p. Filling everything in. E to the 2t. 1 over y1 squared, so that's e to the 4t. And then p is minus 5. The minuses cancel. And I get e to the 5t. So then I have e to the 5t divided by e to the 4t, which simplifies to e to the t. The integral of e to the t is e to the t. So you get e to the 3t. Okay. So for a reduction of order problem, just go with its solution formula, grind it out, and bam, you're done. Okay. All right. It's exactly 10:45. If you came in late and didn't have your test, I have them here.